Welcome to RC Circuits, dB versus phase, FC high. All right, so here is a Bode plot. It represents the frequency domain versus dB. So the vertical axis, the y-axis is in dB, and the horizontal is in frequency. And these are generally broken up between FC low and FC high, which is the minus 3 dB point to the next minus 3 dB point, and that is considered our bandwidth. F1 in this picture represents the FC cutoff low, and F2 represents the FC high or cutoff high. So we know from our previous studies and amplifiers that to look at the high frequency, the F2 in this image, we've got some kind of like stray capacitance, probe capacitance, Miller capacitance that's in parallel with our output, that basically at the high frequency that capacitance starts to short and act like a ground, so or short to ground. And so we can basically simplify all circuits by finding the R Thevenin of that capacitor, capacitance, that stray capacitance or high frequency capacitance. We can find the R Thevenin of that, so we can simplify the circuit down to a simple RC circuit. We know that F2 is representing our FC high. It's at our minus 3 dB point. At F2, our X sub C of all of our stray capacitance, our high frequency capacitance, should be equal to our R Thevenin of that circuit, and that gives us that simple series circuit. We know that X sub C is equal to 1 over 2 pi FC, and that if F2 is equal to, at F2, or our cutoff frequency, X of C is equal to R, then we can substitute out the R and substitute in the frequency cutoff high, which is our F2 in this image, and then we can solve for our frequency cutoff, or F2, equal to 1 divided by 2 pi RC. So we know that F2 is equal to 1 divided by 2 pi RC, which would be our R Thevenin and our high frequency capacitance total. We also know that the voltage gain in dB is equal to 20 log of V out over Vin. And in our previous math book, we learned that we can also find dB by the equation voltage dB is equal to 20 log divided by, or times 1 divided by the square root of 1 plus F divided by our F2, that quantity squared. And where F is any frequency on, basically on the curve, on the high frequency side curve, and F2 is our cutoff frequency, FC high. All right, so we've got two dB formulas, and we can tell, or we can observe, that there's some similarities between these two formulas that we can maybe work and develop a new formula that will benefit us for this example. So if we put both formulas, solve both formulas in terms of delta VDB divided by 20 log, so you can see the next two steps down, I put both formulas. I get, the first one I get is equal to V out over Vn, and the second one I get is equal to the 1 divided by the square root 1 plus F divided by F2, that quantity squared. Well, if those two are equal to delta VDB divided by 20 log, then I can now, I call this step in algebra super substitution. I can make, if they're both equal, then I can also make the outer parts that are equal to those equal, if that makes sense. And that's what that next step is. If AV, or delta VDB 20 log, is equal to V out over Vn, then V out over Vn is also equal to 1 divided by the square root of 1 plus F divided by F2 squared. That's just I call it super substitution method. if this is equal to this and this is equal to this, then this and this have to be equal also. Okay, so now that we've got V out over Vn is equal to 1 divided by the square root of the quantity 1 plus f divided by f2 squared, I can now solve for V out. So now I've got V out in terms of these two equations. V out is equal to Vn times that quantity 1 divided by the square root 1 plus f divided by 2 f2 squared. Okay, so now what if we take and we think of Vn in terms of a percentage, which then gives me a V out in terms of percentage. We call Vn 100%, and then our output would then be something that represents a percentage of the input. Okay, so now we're getting our voltages in terms of percentage. Now we can also get our frequency in terms of F2, our cutoff frequency. And so we know that if we make F equal to 0.25 F2, like that would be back in the bandwidth, right? That would be left of F2. But we can now substitute in the 0.25 F2 into the formula, and we can start doing some math, and we get an answer. Our V out at a 0.25 F2 is equal to 97% of Vn, which we would expect that to be pretty high because you're in the band pass. Now we're just marching up F. We're getting a little bit closer to F2, so we're going to 0.5 and do all the math right there, and we get a V out of 89.4% of Vn. Okay, so if our F is equal to F2, we would expect this to be 3 dB down. We also should know that this would be 70.7%, and you can see the math here, and in fact we get a 70.7% V out at F2. All right, so here's 2 F2. F is equal to 2 F2, and that is referred to as our first octave. 2 times F2, 2 times the cutoff frequency would be our first octave. And we can see that our V out should be 44.721% of Vn. And here is 10 times. Our F is equal to 10 times our cutoff frequency. This is known as our first decade. And we can see, following the math, that we get a V out of 9.95% of Vn. So a very small V out. We're way past the bandwidth. We're way past the cutoff frequency. We've got a little tiny voltage. All right, so we've got our percentage of voltage out, which is V out over Vn, but in percentage at different frequencies relative to the cutoff frequency F2. So we can now put that back into the 20 log formula and then calculate out the dBs at those frequencies. So at 0.25 of F2, we would expect to see a 0.264 dB in the negative drop, which is basically 0. So we would expect that, because it's in our passband, that it would be basically 0. At our 0.5 F2, we're still in our passband, and we see that we get negative 0.973 dB. Now at F2, at our cutoff frequency, we'd expect it to be 3 dB, and we see that it's minus 3.01 dB. At 2 F2, that's our octave. Now we expect that to be 6 dB down. That's known as the 6 dB point. The first octave is known as the 6 dB point, and we see that we get a minus 6.99 dB at that point. And at our first decade, that is known as the 20 dB point, and we see that we do in fact have minus 20.044 dB. Okay, so now we're going to look at phase relationships at those exact points also. So if we've got the phase is equal to the arctangent of VR over V out, the opposite over the adjacent if we're looking at the voltage across the capacitor in reference to the generator. We also know that Vgen is equal to the square root of VR squared plus V out squared, because those two voltages should be 90 degrees out of phase with each other. And so we need to do this square root, the squared and plus the squared, take the square root. Now, if we just keep everything in terms of percentages, or we just call our generator a 1, we can then do the math and solve for VR, where we get a VR is equal to the square root of 1 minus V out squared. Now, if we substitute that back into the original formula, where we've got the phase angles equal to arctan times VR divided by V out, we can now substitute in the VR formula equation into that formula, and we get a phase is equal to arctangent of the square root of 1 minus V out squared divided by V out. And we've got our V outs already for each frequency relative to our cutoff frequency. So we can see that now with that formula, we can just put it in and put in our 97% in fractional form into those formulas. And we see that at our 0.25 F2, angle should be minus 13.664 degrees. Do the same math for the 0.5, we get a minus 26.62 degrees. At our cutoff frequency F2, we would expect minus 45 degrees, and we've got 45 degrees with this math. Now at our first octave, 2 times F2, we've got an angle of negative 63.44 degrees. And at our first decade, we've got an angle of 84.29 degrees. All right, here is all of the data that we calculated, all tabulated for comparison.